Okay, with the advent of going on with all with the things that can be stipulated out here, uh, in this video I'll be talking about I'll be using Schrodinger's equation on a free particle and have a discussion on it. And no doubt this is a one-sided discussion, and I request your good selves to kindly share these videos, like these videos, and share them as much as possible. And to start with, uh, we have the Schrodinger's time independent wave equation as we have del square psi plus 2m by h cross square e minus v of psi, and this is our Schrodinger's wave equation, and this is equal to 0. And this del square is a Laplacian operator, and it can be written down in Cartesian coordinates as the double partial derivative of x plus y plus z. Okay, here I have to have to. So what am I trying to tell you here? Okay, this h cross is h by 2 pi, and this h is Planck's constant, and we have its value 6.62 10 to the power of minus 34 joule second. Now, now talking about a free particle. Now, a free particle is one for which the potential energy has to be potential energy is quite independent of it's quite independent of position, and hence for the sake of convenience it may be set equal to 0. Okay, so since this potential energy is independent of the position of the particle, so for the sake of convenience in boiling down the Schrodinger's equation, we will take this potential equal to 0. So by doing so, this equation will become del square psi plus 2m by h cross square e psi equal to 0. All right, but we better understand that this Laplacian operator is in Cartesian coordinates. It's written in its open form. I can write down it. So it is dou 2 psi upon dou x2 plus dou 2 psi upon dou y2 plus dou 2 psi upon dou z2 plus 2m by h cross square e psi is equal to 0. This should be the case, and certainly we have partial derivatives, and this is a partial derivative equation in three independent variables that we have: x, y, and z. And this may be solved using using a method which is known as separation of variables. And using separation of variables and imposing the boundary conditions. All right, so that this psi is this psi is infinite everywhere in the space, since the particle is free. So psi has to be infinite because this particle we have a free wave packet. This particle is free. Okay, so in doing so, we may write the solution of this equation in the form of some independent functions of x, y, and z. So what should I do is I'll take this psi, which is function of x, y, and z, and that should be borne in mind. That is x of x and y of y and z of z. Okay, so this wave function is the function of these coordinates, where this x of x, y of y, z of z, they are functions of their respective coordinates alone. So this is the function of x alone, this is the function of y alone, and this is the function of z alone. So what would we like to do here is that we would like to substitute this equation that we have, the equation that we have here, and obtain the values. Okay, so what am I supposed to do is that I have to have the double derivative of psi when x is x of x is the function of x alone. So in this case, what would I get is I will have 1 by x of x is understood, and what I will have is dou to x of x divide by dou x2 plus 1 by y dou to y by dou y2. Okay, when we'll take the double derivative of this wave function, say I'll take its first derivative with respect to x, and the other two will behave as independent. They will behave as constants when I'm taking the derivative with respect to the x, and when I'm taking the derivative with respect to the y, x and x will remain as constants for the partial derivative that we have been taking with respect to y. So this is how it goes, and what I will have then will be 1 plus it will be 1 by z dou to z by dou z2, and then plus 2m e, and then I will have h cross square is equal to 0. Okay, that should be the case. This is what we will achieve from substituting. All we have to do is to take the double derivative of this psi with respect to x, with respect to y, and with respect to z. Then what we have to do is we have to multiply this whole equation by x, y, z, and you will have cancellations, and you will be left with 1 by x for the partial derivative of this double derivative of this x, y, and z, and this is what we are going to have in the results. Now, if I write this equation as dou to x by dou x2 is equal to if I take it as minus 1 by y dou to y by dou y2, then minus 1 by z dou to z by dou z2, and then take this energy term. This is minus twice m e by h cross square. Now this is my equation here, okay, and in this equation, you can see the left-hand side is purely in terms of x alone, and if you see the right-hand side of this equation, it's the function of y and z, and is independent of x. There is no x in the right-hand side of this equation. So, so it will be purely empirical to assume here that that both of these sides must be equal to some constant. And what should I start with is that that this 1 by x dou 2x by dou x2 is equal to some constant, say kx. All right, and if this is equal to k of x, then the right hand side of this equation is what? Minus 1 by y dou 2y by dou y2 and minus 1 by z dou 2z by dou z2, then minus 2m e by h cross square is equal to kx square. So for the sake of simplicity, I would like to keep the name for this equation as equation 1. Now, what we have here is that I would like to rewrite this equation and have my left hand side only in terms of y, and use the same approach that I used in the previous case. So what am I going to get here is, okay, if I do that, what will I do? So this is minus 1 by y dou 2 y by dou y2. Okay, if I take this on the other side, then this will become plus, and there I have kx square as its, and what will be left will be minus 1 by y, no, sorry, it will be minus 1 by z dou 2z by dou z2, then minus 2me by h cross square. Okay, this should be the case. This should be the result here. And in the similar way, you can see here in this equation, the left hand side is okay, I have messed up something here which I didn't want, because I have to get this kx on the other side. So if I get it on the other side, then it has to be minus. So I want my left hand side alone in terms of y. So this I'm going to have is minus kx square and minus 1 by z dou 2z by dou z2. Okay, so this is capital Z, and this is small one. Okay, then we have minus 2me by h cross square. Now, the similar kind of situation that we have here, and in this equation, we can see that the left-hand side is independent of z. It does not carry any z, while we can see that right-hand side is independent of y. So therefore, if this equation is to be satisfied, then both the sides of this equation must be equal to some another constant, which I will assume here as y. So what will be that? 1 by y dou 2y by dou y2. This must be equal to ky. Okay, that should be the case. And I think I'm using here square for x. No, I have not used it. I have used kx. This is kx. This is not square. And if you have seen it previously, you will take it as kx. Okay, now, so I will have another equation which is independent of x and z, and I would like to call this as equation 2. Now what I am left with is this minus kx, then minus 1 by z dou 2z by dou z2, and then I have minus 2me by h cross square, and this should be equal to ky. Okay, that should be the case. Now the finality of this thing would be, I want this 1 by z term, I want this to be alone in the left hand side. So for that I will have to rearrange the terms, and what would I get is, I will get 1 by z dou to z by dou z2. I want this to be on the one side, so I will transfer it to the right. So what I will have minus kx here, and then I will have minus 2me by h cross square, and then I will have minus ky. Now, in this equation, again, we will see that the left-hand side is purely dependent on z coordinate. So what would I like to do is that I would like to introduce another constant at this stage, so that this 1 by z dou to z by dou z2 is equal to kz. Okay, that should be the case. And this term, the right hand term, should also be equal to kz. So this equation, so I will have minus kx minus 2me by h cross square minus ky. It should be equal to kz. So that should be the case, and I can write down this, if I shift them, so I can have kx plus ky plus kz equal to minus 2m by h cross square and e. Okay, this should be the case, and for the sake of convenience, let me assume here that this kx is minus 2m ex by h cross square. Okay, that should be the case. I would like to call this as equation 3. Now, moving on from here, if I take the differential equation that I obtained in terms of x, and I write down that equation, so I can do that, and what will be that? That is, you will have dou 2x by dou x2. The 1 by x term will be multiplied, and what you will have, minus 2m by h cross square e x and x. Okay, the denominator one which I have taken that equal to x, and for the kx I have used the value that we have obtained here. For kx is minus 2m by h cross square ex. So what am I going to get is, so for kx I am using minus 2m by h cross square. So what we have dou 2x by dou x2 plus 2m by h cross square. Then we have ex of x, and this is equal to 0. And similarly, we can have the equation in terms of y. What we will have, dou 2y by dou y2 plus 2m by h cross square. Here I will have ey, and then I will have y here equal to 0. Okay, and similarly I will have dou 2z by dou z2 plus 2m by h cross square ez of z equal to 0. That should be the case, and these differential equations have the general solution, and we can think of writing the general solution of these differential equations. So the solution, the general solution Yeah, the general solution for the first one, I can write x, which is function of small x, that is, say, nx sine of under root of 2m by h cross ex, okay, ex, and then we have x. Okay, similarly for y, we will have ny sine of under root of 2m ey by h cross, and then y. Okay, for z of z, we will have nz sine of under root of 2m ez by h cross z. So these are the sets of solutions that we can have for the differential equations that we have obtained, and in every case we have substituted the value of kx, ky, and kz, and if we use this value of kx, ky, and kz, we can have this what we have that equation. Yeah, we have that kx. Yeah, that is kx plus ky plus kz, and what we have substituted for everyone is ex and ey and ez, and what we will have here, we will have e in general. Okay, so we can think of e as the total energy. Now as any sine function that we have is single valued, it's finite, and it is continuous for the real values of its arguments. So I can say that the finite values of x, y, and z in terms of ex, ey, and ez, and hence in terms of e, all of them must be positive. So I can say here that the eigenfunction, or what we may also call it as a wave function. Either you call it as eigenfunction or wave function, or you can say characteristic. My handwriting is very bad. Characteristic function. And energy values of the free particle can be written. So let us try to write down the wave function. So what is the wave function we have? Is we have started with the wave function equal to x of x, y of y, z of z, and we can have this psi equal to n. Okay, it must be n sine of what under root of 2m ex divided by h cross, and then we will have x here times sine of under root of 2m ey by h cross. Then we will have here I have to have y. Okay, then sine of under root of 2m e z by h cross. Here I must have z. Now this n should be nx, ny, and nz, and this is nothing but the normalization constant. So this is normalization constant. Okay, so what we say here, what we conclude here is that this ex, ey, and ez that we have, they are positive, and that is clearly an indicator of the fact that the free particle, has continuous set of energies. It has continuous set of energies. Okay, we can also say set of continuous set of energy levels. And however, the quantization may only occur if the particle is subjected to some kind of constraint. So uh, quantization can only be significant when there is a sufficient constraint that is exerted on this particle, say a particle in a box. And we will discuss that in our next discussion. So then what we can have is we can have the complete wave function for this problem, and we can incorporate, if we are interested, we can incorporate the energy term also in the overall solution of this wave function that we are writing as psi. We can incorporate the terms that are linked with the energy, and we can write down the complete wave function for the particle. For the particle which is absolutely free, moving without any kind of constraint, and potential is not interacting with the potential is not having any interaction with the particle. There's no potential interaction with the particle, and in this case, what we observe is that we obtain what we obtain is that this particle has all possible energies, and when we can think of incorporating those terms from energy and time, like here I can introduce e to the power of minus iota ex t by h cross, and here I will have e to the power of minus iota ey t by h cross. So here I'll have e to the power of minus iota e z t by h cross. So with this, I would like to conclude this talk on applying the Schrodinger's wave equation to a free particle, and it's giving the results where we see that the particle has all possible energies.